It's my pleasure to introduce the next session and our Mr. Campbell Murray, who's the founder of Sookbox, who will help us explore how quantum computing is poised to revolutionize cybersecurity and redefine digital trust. Can we have a huge round of applause for him, please?
Thank you. Good morning. Can you hear me okay? Audio is good? Right. I'm from the UK as well. Quite a few speakers from the UK today. I'm actually originally from Edinburgh in Scotland. I live near London. Hopefully, we do tend to talk fairly quickly where I'm from, so please tell me if I'm going too fast, and I will slow down for you. So, quantum computing. Quick introduction to us as a business. So we're about 9 years old. We've been involved in a lot of tech stuff over the last 8-9 years. We do a bit of client work that involves cybersecurity. We do post-pen test work, that sort of stuff. So we've been getting involved more and more in the cybersecurity from an operating model point of view. And that's opened up this entire world to us around what we think is happening next in cybersecurity. That's why we're here today. So setting the scene, so before we talk about quantum, I think that we're actually living in the middle of a revolution right now. I think we talk about it internally as computing 2.0. And there are effectively 3 megatrends, and if you follow us on social media, you might see us talk about this. We think there are 3 megatrends going on in tech right now that are driving this revolution. And firstly, blockchain. This is obviously as a technology. This enables autonomous, trust-based, independent of human being transactional models. AI, which we're talking about a lot about today, so I'm just going to jump right over that. And then the third piece of this trident of tech, as I call it, is quantum. And quantum is the hardware side of everything we're talking about. And I think what it's going to enable is a step change in the types of problems that can be solved by computing that couldn't be done previously. Now, specifically, and we'll get into this in a minute, quantum doesn't necessarily solve all problems better than non-quantum systems, but what it does do is non-polynomial deterministic time-based models are solved much in a different way completely from traditional computing. So let's dive into that a little bit then. So what that means for us is that some organizations will find quantum solves problems for them on the opportunity side, but all organizations are going to have to deal with quantum from the threat side of things. And you heard some of the speakers, I think Adam was talking about it earlier on. Post-quantum cryptography is real. Every organization on the planet is going to have to face this at some point in the coming years. So let's take a look at how it works. So today, cryptography. Do we have any cryptography people in the room? Any specialists? Okay, a couple at the back. I apologize in advance if I'm dumbing down your otherwise very complex world. But essentially, just to look at this very quickly, all current cryptography systems like SHA-256 are based on prime number calculus. So it's a model that's based on input, not output. You have to know what the input values are to get the answer. So it's a really secure way of encrypting data. SHA, which is probably, is actually the world's most common standard for cryptography. It's been around for a while, since 2001. It's used in everything from SSL certificates on your browser through to things like Bitcoin. It's universally deployed. And it is, as I said before, it's based on 2 prime numbers. Without knowing one of those numbers, it's almost impossible to de-encrypt an SHA code. So try and give you some context. People often say, well, how long does it take to crack these things? And it's hard to answer the question because you have to ask another question, which is how complex is the character structure? But just to give you some examples, if you use a very simple 6-character number-only encryption method, you can crack it with today's computing technology, pre-quantum, almost instantly. So it's worthless. But you make it a complex structure of numbers, letters, characters, and you take it all the way up to the 64-bit full function at 20 characters, you're talking quintillions of years to crack it. So the complexity of the password system's a massive part of this. Now, computing 1.0 machines are binary. This means that all problems are solved using a trial and error type model. And when you go into the quantum space, it doesn't work like this. Because quantum, if you know much about quantum physics, a quantum value can be anywhere between 0 and 1. So a qubit in a computer gate isn't just a 0 or 1 value, it's every number in between, every possible number in between. That means that in real time, a quantum system can see the value range from 0 and 1 to infinity. Sounds complex, a bit mathematical, but what it means is that when you try and do a problem, and I'll show you in a second with an example of the maze, when you look at a problem with options, a quantum computer can try multiple combinations of outcomes at the same time, in real time. So this little video, you just play this for me? I think it's got
In a normal search, our agent tries to search every path randomly to reach the destination, and we cannot claim that the path we find is the shortest until we visit the entire search space.
So maze is
However,
a good example.
with quantum search, you start with one agent, but whenever the agent encounters multiple paths, we send one agent to each new path. This allows us to search more quickly. The twist in this situation is that all those agents you see on the screen are just one single agent in multiple places. This phenomenon is known as quantum superposition. At the end, when we find the solution, all the other agents disappear, and the real existence of the agent is at the destination. It's strange, but that's how quantum computers are going to work. When we compare agents, we can see that quantum computers can easily win. Even with an increase in problem size, the complexity of the problem for a quantum computer will be linear. Share your thoughts on this.
So if we take a maze as just a simple visual representation of what I'm talking about, you can see how this would apply to trying to de-encrypt an algorithm that's data at rest or data on the move. But that little visualization, what you saw there in the bottom screen, was if you imagine trying to hack the code and you've got more combinations than there are atoms in the universe, clearly, a traditional computer would have to try every combination, and it would just never get there. Whereas in the quantum world, because each time it gets to a junction point, it can try every possible value range within 0 and 1, you have an infinite number of attempts to solve the problem. So that's what I mean by an NP mathematical problem model. And so when you look at the post-quantum cryptography world and what that means to businesses, one of the big conversations we get into is this idea of Q-Day. I think Adam mentioned it earlier on as well. So Q-Day, we'll get into in a second, but it's widely defined as the day when a quantum computer is powerful enough to crack an algorithm like SHA-256. And there's all sorts of debates about when that's going to be. And the thing that got me really interested in quantum was I saw a presentation from IBM about this, and they were showing the timelines of the average consensus of prediction when Q-Day will come. And every single time they did the maths, the date came forward. It never went back. So you'll hear all sorts of theories on when this is good to come. The most optimistic, or pessimistic, depending on how you look at it, the most pessimistic date might be 2 to 3 years away, and the most optimistic might be 10 years. No one knows. No one can tell you the answer. Everyone's got an opinion in the subject, in the field, but the reality is it is coming, and no one knows when. So IBM, for example, you may have seen this article in Forbes, they think they'll get to about 1,000 qubit fault-tolerant equivalent system by 2029. Now, the only defense against this is that the bad guys don't get their hands on the hardware. I think that's an unrealistic expectation, that this won't appear on the dark web somewhere in the world in a reasonable time frame, within sort of 5-10 years. So, what does that mean? So, I think, again, someone used the analogy of Y2K earlier on. This is a bit like Y2K, but without a specific date when it's going to happen. No one knows. So the way I look at this, and the way we talk to customers about this, is the sooner you tackle this, the sooner you make your data post-quantum cryptography safe, PQC safe, the sooner you can rest a little bit on this. Because we talk to customers a lot about this idea of when this is coming, and because they've got other more pressing issues, it's easy to kick this can down the road and deal with it later. My counter view to that would be that if your data gets stolen today and it's encrypted, you may take some comfort from the fact that the data is protected, but at some point in the future, that data is going to be de-encrypted. And so it's a harvest now, decrypt later model. And so the question then becomes, how time sensitive is the decay of your data model as you look at it going forward? So it's very topical at the moment. Obviously, the number of cyber attacks in the media increasing on a daily basis. Some very high profile ones in the UK where I'm based. Jaguar Land Rover looks like a £2 billion loss, uninsured. Marks and Spencer's, 300 million loss because of cyber attacks. So this is an increasingly visual representation of how big this problem is. And one of the things that we always say to customers is clearly threat detection and preventing these things happening is, of course, your primary objective. But if you get hacked and your data is taken, the integrity of your business is based on whether or not that data is in the clear or is protected. So everything you can think of pretty much relies on this kind of encryption cryptography. And it's right across the banking system, the telecom system. Everything you can think of is affected. Now, I often talk about this in the context that you see in movies when someone steals a load of money from a bank and they get on the getaway car and they're heading away from the bank and the cash bag explodes on them and the red dye goes all over the money. I often say to customers that I think PQC is a little bit like that. It's a digital equivalent of making sure the data, if it is taken, is worthless to the bad guys. That's ultimately what you're trying to do. You want to prevent it getting taken? Of course you do. But if it does go, you want to make sure that it's just gobbledygook and absolutely useless to the guys that have hacked into your system. So, data sensitivity. If you've got a business, let's say, for example, you're doing a lot of credit card e-commerce transactions, and you're storing your PCI PED compliant, you're storing your customers' credit cards, and you get your data is breached and stolen today. In 2 years' time, that data is probably going to be worthless. The credit cards all have expired. There's a low value to the bad guys on what is in that data structure. But if you're dealing with a family office, you're a law firm, you're a tax accountant, you're dealing with multi-generational data, then the data stolen today, in 5 years' time, will be just as sensitive as it is right now. So, we work with IBM. We're an IBM cybersecurity partner, and we launched a service in the last few months, which we're calling Quantum Ready, and it's, as you can probably imagine, very focused on a quantum and AI-driven perspective on your cybersecurity profile. It does not replace every aspect of cybersecurity. We're just focused on getting you PQC ready. So, if I just quickly play this little video for me.
The modern
Some
world
audio,
is a
please.
technologically advanced marvel. We do almost everything online and depend on IT security professionals to secure our information in an ever-increasingly complex digital economy. Almost every bit of data in the world is encrypted on databases, and the current industry encryption standards protect this, so that even if your information is stolen, it is useless to the hackers that stole it. That is all about to change with the onset of quantum computing. Quantum computers don't work like standard computers and have the potential to unlock today's ultra-secure cryptographic security algorithms in hours. The good news is that there are solutions on the horizon, and that is why Soupbox has launched Quantum Ready. If you want to learn more about what quantum means to you and how to become quantum ready, get in touch with Soupbox today.
So, when we talk about post-quantum cryptography, just to give you context in this one, 1,000 qubits stable is the magic number that we tend to talk about in this space. So when we get to 1,000 qubit stable system, we think that an SHA-256 algorithm would be de-encrypted, even if it's fully loaded, de-encrypted in about 4 hours. The guys at Google had a look at this recently and published a document. They said that the best guess is using the best systems that are available in the world today, there's about 10,000 years to crack a full SHA-256 algorithm. But with a 1,000 qubit stable system, the maths suggest that that's going to come down to about 4 or 5 hours. So it's an absolute game changer in the time involved in de-encrypting this. So we've launched a service to help customers prepare for a PQC world. So very straightforward. We work with customers to understand their own environment, to get their heads around what it is they're trying to achieve, what data is sensitive. One of the reasons why we partner with IBM is that they've, and I think someone asked a question earlier on about commercial software. IBM's Guardium software suite, I think, is best in class. I think IBM, it's fair to say, are probably the world's commercial leader in quantum. There are 3 out of the 4 lattice algorithms that NIST have approved came from IBM. They're right at the front of this, and the Guardium system has been built to put in place a lifecycle management plan that's post-quantum safe. Everything about it is about understanding your risk and exposure to quantum and AI, and then putting in place a plan to fix it. So Some of the customers, this one's been slightly, I hope it's anonymized. Some of the customers we were talking to, when we start talking about their IT estate, one of the big questions we get into is, do you know your IT estate? How big is your shadow IT estate? Do you understand what you're dealing with, first and foremost? Because when you start to look at an organization's complexity and work out where to focus and prioritize your time, it can get nebulous in size. There's a really interesting bit of data which I was shown recently. It's the number of homegrown applications that an organization will have in its infrastructure. And there's almost like a three-way model in this. The number of years you've been in business, how global you are, and how active you are from an M&A perspective, those three factors drive up the complexity of your IT estate. And what I found was amazing is the number of organizations with more than 10,000 homegrown applications in their IT estate. It's actually quite large, especially telecoms companies, utilities companies, and airlines. Some banks have over 10,000 applications inside their IT estate. So when you're trying to think about where's my data, where's it sensitive, where's it shared across these systems, just getting to this point alone is a fairly significant undertaking. It should not be underestimated. Talk a little bit about encryption. So the good news is that there are now solutions in place. If you got to a point where you identified where your data was, and you said, right, I want to go ahead and make this post-quantum safe, then the algorithms are there now. The lattice algorithms that are out, the NIST approved standards, I said there's 4 of them being approved already. They're widely available now to deploy. So the really good news is there is a solution that we believe is post-quantum safe. Now, will it be safe forever? Probably not. But this is going to buy a lot of time. This is going to buy you 50 years potentially. So we are now talking to customers about putting this into their system right now. And I think it's the future of where we're going with this. Now, let's just skip over that, that's fine. So I'll touch on this very briefly. Why is a lattice algorithm safe compared to a non-lattice model? Well, essentially it comes down to this idea that in order for you to guess the vector in the mathematics, you have to use intuition. And that's something that obviously a computer's not very good at doing. So essentially, in a pure brute force attack model, you can work your way through the model and get to an outcome. But when you rely on intuition to work out the vector path that's fastest, you can't do that. If you want to know more about this, I'm happy to talk to you over a coffee later on about this. So, big message for us is quantum is real. It's here. It's now. We're seeing a timeline that's potentially between 2 and 10 years away before your data is potentially post-quantum hackable. So QD is coming. And as soon as our customers start building a plan to deal with it, the better equipped they'll be to protect themselves when that inevitable thing happens. So I think for our point of view, contact details up there. If you want to have a chat with me about this, please come and grab me throughout the day or take my details and get in touch. But from our point of view, what we're really interested in now is just talking to organizations who are at the thinking edge of this and starting to see we need to put a plan in place. We'd like to have a view on this. And yeah, we'd be more than happy to come and have a chat with you. Thank you very much.